So for question number 1, you were asked to graph the number of volts produced versus time in minutes. So time goes on the X with the unit of minutes. Number of volts produced goes on the Y. You could have graphed this by hand or on a computer. Either is fine. Here, I also demonstrate the importance of minor grid lines. So I go by every 1 here and go by every 20 here. Once you have your data points plotted, then you draw a best fit line. So I had this at the trend line for me. To get the slope, you identify 2 points that appear on an intersection of a grid line. So I chose that point there and that point there. Now the first point, by reading my graph, has coordinates of 12, 400, and the second point is 18, 600. Those are my x, y values. To get the slope, you're going to do change in y divided by change in x. So your slope is going to be 600 minus 400 divided by 18 minus 12. And you're always going to reduce it. You never leave it as a fraction. And I get 33.3. And the unit for that is volts per minute, which is a production rate. Don't forget all your rules for graphing, where you need to have an appropriate title in y versus x. You need to have your axes labeled with a unit. You need to have the appropriate minor grid lines in an interval of 1, 2, 5, or 10, something that makes sense. A trend line that represents the line of best fit. If you're graphing this on the computer, you would also include an equation for the line and the r squared. Question 2 involves scientific notation. You start where the decimal is, and then you move the decimal so you have one non-zero digit to the left of the decimal, because remember, the first part of scientific notation has to be between 1 and 10. So if the decimal is here, I would move it 1, 2, 3 places. So I would get 1.251 times 10, and the number of places you've moved it becomes the exponent, and the unit is grams. And if you're taking a big number and making it into a more manageable number, your exponent's going to be positive. If you have a smaller number, like this next one, you move the decimal over till you have one non-zero digit. So you get 4.85, but now it's times 10 to the negative 3 liters. Now to expand it out, to go the other direction, 3.75 times 10 to the negative 3. I need to turn this into a decimal number, a 0.0 something. So the easiest way to do this is, my number here is a 3. It's negative 3. Take the absolute value from that, which is 3. Take 1 away, 2. I'm going to need 2 zeros in front of my number. So 0.00375 unit is grams. And so basically I took this decimal and I moved it back 3 places. So you can do it either way. Now, if I'm taking a big number and expanding it back out, so positive exponent, I need to move the decimal 4 places, 1, 2, 3, 4. Or this value is a 4. I have 2 past the decimal. 4 minus 2 is 2. I need 2 zeros at the end of the number. So 78200, and the unit is centimeters. All right, so significant figures. So you either need to know the rules for zeros. So zeros at the beginning of a number, or your leading zeros, never count. Zeros at the end of a number, your trailing zeros, only count if there's a decimal. And zeros in the middle of a number always count. Or if your teacher taught you the Atlantic Pacific rule, here's my sad little United States. If your Pacific is here and the Atlantic is here, if the decimal is present, you start at the Pacific side, go left to right, and start counting when you hit your first non-zero digit and count everything after that. If the decimal's absent, you start at the Atlantic side, go right to left, start counting at the first non-zero digit, and then count everything that follows. So for A, the decimal is absent. So I'm going to start here, move across. I start counting at the 2, 1, 1. I have 3 significant figures or zeros at the end. Never count if there isn't a decimal. The next one, decimals present. So I start at the Pacific side. I start counting at the 8. So 1, 2. Or zeros at the beginning, never count, and the 8 and the 2 are significant. 17.09, the decimal's present. So I'm going to start at the Pacific side. So I start here. That's the first non-zero. I do 1, 2, 3, 4 significant figures. Zeros at the beginning, zeros in the middle, always count, and non-zero always count. Decimals present, so I start at the Pacific, 1, 2, 3, 4. All non-zero digits are significant. There's no zeros there, so there are 4 significant figures. So now we're going to look at the rules involving mathematical calculations and significant figures. Addition and subtraction is the same rule. You can remember plus is place. You're going to round to the least significant place. Multiplication division is the other rule. Multiplication is many. You look at all the significant figures. So for the first question, I have 2 past the decimal, and I have 4 past the decimal. 2 past the decimal gives me the least significant place. 2 is smaller than 4. I round to 2 past the decimal. So I hit it into my calculator, and then I round so that I have 2 significant digits past the decimal. Number 2 is division, and that's the same as multiplication, which is many. I look at all the significant figures. So I have 4 total and 3 total. 3 is less than 4, so I hit it into my calculator, and I round to 3 total significant figures, 3.62 grams per milliliter. 3 is multiplication, so I look at the total significant figures, 4 total and 6 total. 4 is smaller, so I need to round to 4. But when I hit it into my calculator, I get 467200. So what you need to do is you need to put that into scientific notation. So your answer is going to be 4.672 times 10 to the 4 centimeters squared is the unit. Now for the last one, we have a mix of operations. I have addition, subtraction, and I have division. So the first thing you're going to do is you follow order of operations. You follow your PEMDAS. So I add this together and I get 11.701. But that rule is going to be placed. 2 past the decimal, 3 past the decimal. So this would round to 11.70. Then I take that and I divide that by 4.8 hours. Multiplication is many. Then I look at the total. So I have 4 total and I have 2 total. 2 is the smaller number. So I need to do the least number of significant figures there. I hit it into my calculator and I get 2.4 meters per hour. Okay, reading equipment. This has to do with precision and reporting the correct number of significant figures. Whenever you look at a piece of equipment, you're going to look, where are the smallest markings? What is the increment? Then you have to estimate one place beyond that. So for these graduated cylinders, we're going to look. So here I have a mark at the 20 and I have a mark at the 30. My smallest marking goes by every 1. So therefore, I need to estimate to the 0.1 position. Now you're going to look at the bottom of the meniscus. So the meniscus is right here. I'm going to read the bottom of that. Now, if you believe that this is exactly on the line, which is what I think I said it was, you're going to put 25.0 milliliters. If you think it's a little bit above the line, then you can put 25.1 milliliters. But remember, that last number is an estimate, so therefore there's going to be variation in it. The point is you have to have one place past the decimal. The next one, we have a 25 and we have a 30. Our increments are every 1, so I need to estimate the 0.1 position. So this is going to be, this is the 36 mark, that's the 37. It's about halfway between. So I would say it's about 36.5 milliliters. Again, you have to have it to the 10th position. The next one, we have a mark at the 5 and a mark at the 6, and therefore our increments go by 0.1. So I need to estimate to the 0.01 position. So here it's going to be between 0.54 and 0.55, and I said it was about 5.47 milliliters, and you need 2 past the decimal. And then the last one, I have a mark at the 10, a mark at the 20, and increments every 1. So I need to estimate to the 0.1. And I said this was about 14.8 milliliters. Question 8 involves calculating a density. Density is mass divided by volume. In the problem, it tells us that the metal has a mass of 25 grams. So I need to calculate the volume. Well, it tells us that I put it into water, and the water level goes from 13.5 to 21.5 milliliters. So the volume of the metal is 21.5 minus 13.5, or 8.0 milliliters. I can take that value and put it below my mass. Mass divided by volume gives me the density. I'm going to need 2 significant figures, and I get 3.1 grams per milliliter. Now, protons number neutrons and electrons. So you have to remember the 2 different types of notation. This is hyphen notation right here. The number after the hyphen is your mass number. And the mass number is protons plus neutrons. In the nuclear symbol, all the information is given to you. The top number is the mass number, which is protons plus neutrons. The bottom number is the atomic number, which you can also get from the periodic table. That's number of protons. And then the top right number is the charge, which is protons minus electrons. So if I have 64 over 29 copper, and I want to know protons, electrons, neutrons, the bottom number tells me protons. So I have 29 protons. Neutrons are going to be mass number minus atomic number. This is already set up like a subtraction problem. So it's 64 minus 29, so I have 35 neutrons. Electrons, there's no charge there, so it's neutral. When it's neutral, protons equal electrons. Now for 118, I have to look at the periodic table to get my number of protons. So I find the whole number on the periodic table, and that's 50. To get my neutrons, it's mass number minus your atomic number. So it's 118 minus 50, so I get 68. There is no charge indicated here, so therefore it's neutral. It means I have 50 electrons. For the oxygen ion, eight protons, because that's the number on the bottom. 16 minus 8 gives me 8 neutrons. And if it's -2, it means it gained 2 electrons. So I have 10 electrons. Now for magnesium, 12 protons, because the number on the bottom tells you number of protons. 24 minus 12 gives me neutrons. Plus 2 means it's lost 2 electrons. And it means it has 10 electrons. Question 10, refer to the answer key. Gives you all the information you need to know for charge, mass, location, etc. for the subatomic particles. Question 11, the average atomic mass of boron, if it exists, as a certain percentage of boron 10 and a certain percentage of boron 11. That's a weighted average. Remember, weighted average we don't do as a traditional average or a mean. What you need to do is you need to take into consideration how many isotopes there are, the percent abundance, and the mass of each isotope. So for 11, what we're going to do is you do percent times mass plus percent times mass, etc., until you use up all of the isotopes. So the mass is going to be 19.9% times the mass of boron 10, which is 10.013, plus 80.1% times the mass of boron 11. If there was a third isotope, you do percent times mass a third time. Don't forget these are percentages, so you need to at some point divide by 100. So either divide the percentages by 100 before you multiply, or hit this all into your calculator and divide by 100 at the end. And when you're done, you get 10.81 AMU. All right, number 12. How many grams of carbon are in 225 grams of methane? There's several different ways to do this. The easiest way is to just treat this as a percent composition. So the first thing you can do is calculate the percent carbon. So that's going to be the mass of carbon using your periodic table, so 12.01, divided by the total mass, which is the mass of carbon, plus 4 times the mass of hydrogen, and then multiply that times 100. And we get 74.83% carbon in any sample of CH4. Then, if I know I have 225 grams of CH4, 74.83% of that is carbon. So I multiply that times 74.83%, and I get 168 grams of carbon. 13 is a percent composition, which is essentially what we did in 12, but just with one more step. And it's going to be the mass of the individual element divided by the total molar mass. So the percent iron is the mass of iron from the periodic table divided by the total mass, which is 55.85, plus 2 times the mass of oxygen, plus 2 times the mass of hydrogen. And then I multiply that times 100, and I get 62.15% iron. The percent oxygen is going to be the mass of oxygen, which is 2 times 16, divided by the total mass, 55.85, plus 2 times 16, and then multiply that times 100, and I get 35.61. And then the percent hydrogen, I do exactly the same thing, but the top number is my amount of hydrogen. So 2 times 1.01 divided by the same value that's there. I'm just saving myself a little writing. Multiply by 100, and I get 2.24% hydrogen. When you're done, remember all of these have to add up to 100%. And if they do, you most likely did it correctly. Question 14 involves empirical and molecular formula. Most teachers use a poem where we have percent to mass, mass to moles, divide by smallest, multiply till whole. So remember, the idea is you want to convert everything to moles, then divide by the smallest to get the mole ratio, and then from there we can get the empirical formula and potentially a molecular formula. So we have a substance that has 39.97% carbon, 13.41% hydrogen, and 46.62% nitrogen. So the first thing we're going to do is we're going to assume 100 grams, and my percent values become grams. So carbon, I have 39.97 grams. Hydrogen, I have 13.41 grams. And nitrogen, I have 46.62 grams. Percent to mass, done. Now, mass to moles. So I use the molar mass of carbon, get that from the periodic table, and I get 3.328. Then hydrogen, 1 mole of hydrogen has a molar mass of 1.01 gram, and I get 13.28. and nitrogen has a mass of 14.01 grams, and I get 3.328. Now remember, for this step here, do not round too early. If you round too early, oftentimes you will get errors because you've dropped significant figures. So I've done mass to moles. Now I divide everything by the smallest, which is 3.328. And I get 1, 4, and 1. Now remember, if you get like 1.5 or 2.5, you then have to multiply by a factor to get a whole number ratio. So I've divided by smallest. I don't need to multiply till whole. These numbers become my subscripts for my empirical formula. So my empirical formula, which is the simplest whole number ratio, is CH4N. Now, the problem says, what is the molecular formula? Now remember, the molecular formula is how this exists in nature, and it's multiples of the empirical. In order to figure out how many empiricals I have, I take the molar mass of the molecular divided by the molar mass of the empirical, and that will tell me how many empiricals I have. So the molar mass of the molecular is always given in the problem. The molar mass of the empirical is 30.06, and I get that by 12.01 plus 4 times 1.01 plus 14.01, all from the periodic table. So when I take 16 and divide by 30, I get 2. So that means there are 2 empiricals in the molecular. So I multiply all the subscripts times 2. So I get C2, H8, N2, and that is my molecular formula. All right, question 15, we are completing nuclear reactions. So remember, all the top numbers need to add up to the same value on both sides. All the bottom numbers need to add up to the same value on both sides. So if I have 14 on the left, 14 on the right, the only value that I can have here is a 0. If I have 6 on the left and 7 on the right, this has to be a -1. 0 over -1 is an electron or a beta particle. The second one, my total on the right is 189. So therefore I have to have a 2 here. Total on the bottom is 76, which means I need to have a 1. 2 over 1, the element that has an atomic number of 1 is hydrogen. Okay, next one. Total on the right is 22. So I have to have a 0 over here. Total on the bottom on the right is a 10. Has to be a -1 because 11 minus 1 is 10. That is also an electron or a beta. And then the last one, the missing number here is 214 over 82. I look on my periodic table. The element that has an atomic number of 82 is lead. Okay. Symbols for alpha, beta, gamma. And alpha is 4 over 2 with the alpha symbol, or 4 over 2 helium. Beta is 0 over -1 with the beta symbol, or 0 over -1 electron. And gamma is 0 over 0 with the gamma symbol. Alpha is the least penetrating. Gamma is the most penetrating. Okay, half-life. You have 2 ways you can do half-life. You can use the formula or you can use the chart. Now the formula is the amount at time t is the initial amount times 1/2 raised to the n, and n is the number of half-lives. So the number of half-lives is the time elapsed divided by the half-life. So if we're going to use the formula for this, the amount at time t, which is what we're asking for, we initially have 120 grams times 1/2. My n, 10 years has elapsed. Half-life is 2.5. So 4 half-lives have elapsed. Now I can plug it into the formula and I get 7.5 grams. If you don't want to use the formula and you have an even number of half-lives, you can use the chart. So remember, it's number of half-lives, time, and amount. You always start at 0 with number of half-lives and time. And at time 0, I have 120 grams. After 1 half-life, 2.5 years has gone by, I have 60 grams remaining. 2 half-lives, 5 years has gone by, 30 grams remain. 3 half-lives, 7.5 years, 15 grams. 4 half-lives, 10 years, which is what I'm trying to get to in the problem, 7.5 grams remain. So either one of these methods will work. The chart only works if you have an even number of half-lives. If you have a decimal number of half-lives, you have to use the formula. Don't forget, it's crucial that you put 0 at the time and 0 at half-lives if you're using the chart. Ionic compounds involve doing crisscross. So you need to know your periodic table, that group 1 forms +1, group 2 forms +2, group 13 metals +3, group 15 -3, 16 -2, 17 -1. You also need to know how to work with polyatomics. So sodium and carbonate. Sodium is an element. It's group 1. It's got a +1. Carbonate, we're going to learn this when we get to nomenclature, but if it ends with ATE, it's a polyatomic. It's CO3, and it's got a -2 charge. Take the 2, bring it down, the 1, bring it down, and it becomes Na2CO3. You do not use parentheses if there's only one polyatomic. Iron 2 and dichromate. Remember, the 2 is there to tell you that the iron has a charge of +2. It's a transition metal, therefore you cannot use the periodic table to predict the charge. Iron, therefore, is a +2. Dichromate, you look on your polyatomic sheet, and it's Cr2O7, and that's got a -2 charge. Now remember, if the values are the same, just opposite, the charges cancel out. It overall has a charge of 0. You drop the charges and just push it together, so you get Fe, Cr2O7. Aluminum and sulfur. Aluminum's group 13, sulfur's group 16. The 2 comes down, the 3 comes down, you rewrite it, Al2S3. Ammonium and thiosulfate. Ammonium is the only polyatomic that you're going to be working with. Ammonium is NH4 with a +1 charge. Thiosulfate is S2O3, and that has a -2 charge. The 2 comes down, the 1 comes down, so I need 2 NH4s. Therefore, I need to put that in parentheses, and I only need 1 thiosulfate. Calcium and bromine. Calcium is +2 because it's group 2. Bromine will be -1 because it's group 17. It becomes CaBr2. Tin 4. IV is 4, which means tin has a +4 charge. Oxygen's group 16 has a -2. Now, this is one that if you crisscross, you need to reduce. The answer, if you crisscross, you get SN2O4, but for ionic compounds, it needs to be the lowest whole number ratio, so it's SNO2. All right, electron configuration. You either need to know how to use the periodic table, or you have to write out your diagonal rule. To write out the diagonal rule, what you're going to do is the first column, 1, 2, 3, you're going to go down. It doesn't matter how far you go. We can go to 7. They're all S's. The second column, you start with a 2. They're all P's. Third column, start with 3. They're all D's. Now, technically, there is no 6, 7D, but it really doesn't matter because you're not going to go that far out. Fourth column, start with 4. They're all F's. Then you're going to draw your arrows. And they go numerically in order. So 4, 5, 6, 7, 5, 6, 7, etc. Then what you're going to do is you are going to copy the noble gases right above the 2s. So we're going to have helium, because this is to help you with doing the abbreviated, then neon, then argon, krypton, xenon, radon. Now, if you're using the diagonal rule, which we will do with selenium, so you look on the periodic table, you find selenium, it has 34 electrons. You always start at the top, so we're always going to go 1s, then 2s, 2p, 3s, 3p, 4s, and you follow the diagonals. So for selenium, we start with 1s. You need to know that an s can hold 2. Then we go to the 2s, which can hold 2. Then we go to the 2p, which can hold 6. And you basically just keep going until you have used up 34 electrons. So 3s2, 3p6, 4s2, 3d10, 4p6. Actually, it's 4p4. So the key might say 4p6, it's 4p4. Now, to do the abbreviated on the periodic table, you find the noble gas that's closest to its atomic number without going over. So that's going to be argon. Now, by writing argon, you have written the electron configuration for the first 18 electrons. So you basically need to write 16, you need 16 more electrons beyond argon. Now, how do you know where to start? That's why we wrote these over here. So if argon's your base, you start with the 4s. So it's going to be 4s2, 3d10, 4p4. And then you are done. Now, copper, you need to remember, is an exception. Copper, remember, 1 electron from the s goes out to the d. So copper has 29 electrons. And if I do this electron configuration out, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Now, if we do that like we've been doing all along, that's what we would get. But the thing is that 1 electron goes from the s out to the d. So this becomes, instead of 4s2, 3d9, it ends with 4s1, 3d10. Now, to do the abbreviated, I'm trying to erase this, and this doesn't erase. This goes with the selenium. You go up 1 all the way to the right. Argon is my base. It ends with 4s1, 3d10. Now, for the ions, iron 2 plus, if I do the electron configuration out, iron has 26 electrons, but if it's a +2, it means it then has 24 electrons. If I do out the full electron configuration, I get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. When you are forming ions where you're removing electrons, you remove electrons from the highest occupied energy level first. So the 4s electrons get removed when you are forming the Fe2+. So it becomes 3s2, 3p6, 3d6. So you have to remember you remove the highest occupied energy level electrons first. Now, rubidium ion and bromine ion, you need to know that rubidium's group 1, it would form a +1. You need to know that the bromine is in group 17, it would form a -1. So for both of those, you are writing the electron configuration essentially for krypton. You can refer to the answer key for those. All right, the orbital diagram, you have to draw out the orbitals and label them. So silicon has 16 electrons. So the first two would go in the 1s. And remember, you start lowest energy first. That's Aufbau. And the electrons to exist in the orbital together, they need to be paired. 2s comes next. Then we fill the 2p. But remember, when we fill the 2p, Hund's rule says 1 electron in each orbital until they're all half full. Then Pauli says we need to have opposite spin. So that's 10 electrons. 3s comes next. Then 3p. And you're going to go up and up. You can have an empty orbital. Okay, and the reason why we do this is because we want to identify the unpaired electrons, because it's the unpaired electrons that are going to help us make predictions with bonding. The potassium ion, you can refer to the answer key. Okay, periodic law basically states that when we put elements in order of the increasing atomic number, we get this repeating pattern. So elements' properties are functions of their atomic number. Now you need to know your trends, your period trend and group trend for atomic radius, electronegativity, reactivity, ionization energy. So as you go across a periodic table, so period goes across. So as you go across a period, your radius is going to decrease. This is because we are adding more protons and more electrons, but the electrons are being added within the same energy level. So therefore, the distance is essentially constant. We are increasing the charge, increasing the force. So it's causing it to decrease in size a little bit. We're not adding energy levels, we're adding electrons to the same energy level. And we get that effect of charge in Coulomb's law. It has a greater effect than the increasing energy level. Your electronegativity is going to increase going across. Your ionization energy generally increases going across because the atoms are getting smaller. As they get smaller, the electrons are closer to the nucleus. As they become closer to the nucleus, they're held more tightly. It takes more energy to remove them. Your reactivity for your nonmetals is going to increase. The most reactive nonmetal is fluorine. For your reactivity for metals is going to decrease. Francium is the most reactive metal. Now, as you go down a group, groups go up and down. As you go down a group, the radius increases because we're adding more energy levels. Those outermost electrons are getting further and further and further from the nucleus. Your electronegativity decreases, your ionization energy decreases because the atom is bigger, the electrons are further, they're held more loosely, it takes less energy to remove them. Your reactivity for the nonmetals is going to decrease as you go down a group. For your metals, it's going to increase as you go down a group. So remember, most reactive metal is francium, most reactive nonmetal is fluorine. For electronegativity, fluorine is the most electronegative with a value of 4, and your noble gases do not have an electronegativity value because generally they do not react. Xenon does have a little bit of electronegativity value because it will form a couple compounds, but generally no electronegativity values for your noble gases. Okay, circle the element ion with the larger radius. So calcium versus calcium 2+. So calcium 2+, we've lost electrons, therefore it gets smaller. So calcium has the larger radius. O or O2 minus. Well, O2 minus, I've added electrons. I have more repulsive forces. O2 minus is going to be larger. Manganese or technetium. Well, manganese is here, technetium's here. As you go down a group, atoms get larger, so technetium has the larger radius. And then iridium versus platinum. Iridium versus platinum. As you go to the right, the atoms get smaller, so iridium has the larger radius. All right, larger ionization energy, rubidium or strontium. Strontium's smaller. It's going to have a larger ionization energy. Aluminum or gallium. Aluminum's here, gallium's here. Aluminum is smaller. It's going to have the larger ionization energy. Iodine or bromine. Move this around. Iodine is here, bromine is here. Bromine is smaller. It's going to have the larger ionization energy. For 26, larger electronegativity. They are the same trends as ionization energy, so it's going to be strontium and aluminum. But now I'm looking at iodine or argon. Iodine or argon. Well, argon's a noble gas. There is no electronegativity value. So clearly, iodine has the larger electronegativity. That's kind of a trick. It's an exception to the trend. 427, make sure you know the different parts of the periodic table. So alkaline earth, I'm just going to kind of draw arrows, I think, for this. So your alkaline earth is group 2. Your alkali is group 1. Your transition metals is this section right here, which is also the D block. Your inner transition metals are down here. That's also the F block. Halogens are group 17. Noble gases are group 18. The metalloids, sometimes called semimetals or metalloids, depending on how you say it. Remember, they border the stair-shaped line. So your metalloids are going to be along here, with the exception of aluminum. Your nonmetals are everything to the left of that stair-shaped line. I'm sorry, your metals are everything to the left of the stair-shaped line, and your nonmetals are everything to the right of the stair-shaped line. Last two things. This right here is the S block, the first 2 columns, and this right here is the P block, the last 6 columns, except for helium, which technically is not in the P block. All right, dimensional analysis, so conversions between units as well as the mole. So remember, the whole point of this is keeping track of the units because it tells you whether to multiply or divide. So first thing you're going to do is identify the conversions. So 4.21 years to minutes. I'm going to go year to day, day to hour, hour to minute. You're then going to start with the number and unit given in the problem, so 4.21 years. Draw your train track. The unit year comes down. Unit I want to get to goes to the top. 1 year, then I fill in my relationship, has 365 days. Unit year cancels. Day comes down. Hour goes to the top. 1 day has 24 hours. Day cancels. Then hour comes down. Minute goes to the top. 1 hour has 60 minutes. Remember, put the 1 by the bigger unit. Hour cancels. Now I just multiply all the values across the top using significant figures. 2.21 times 10 to the 6 minutes. Now, millimeters to inches. You need to know your prefixes. You need to know millimeter, centimeter, kilometer, and then you also need to know micro, nano, pico. So you need to know those relationships and be able to set them up into conversion factors. So go back and look into your notes. All right, I have 1589 millimeters, and I want to get to inches. Now I know that there's 2.54 centimeters in an inch. So now I need to get from millimeters to centimeters. So I put this over 1. Millimeter comes down. It's best to always go to the base or go to the unit. So millimeter to meter. Put the 1 by the bigger unit. Meter is bigger. And there are 1,000 millimeters in a meter. Now meter can come down. Centimeter can go to the top. Put the 1 by the bigger unit. 1 meter is 2.5. No, it's not. 1 meter is 100 centimeters, and those can cancel. Now centimeter comes down, inch goes to the top. 1 inch is 2.54 centimeters, and centimeters can cancel. You will get conversions on the test of things that are not common, but you do need to know your prefixes, and you do need to know common relationships, feet to miles, inches to feet, etc. So multiply across the top, multiply across the bottom, divide top by bottom, and we get 62.6 inches. C involves converting a complex unit. So if I have 65 miles, now I have a unit in the denominator. That's per 1 hour. So I need to make 2 conversions here. So the first thing I'm going to do is convert the time, but instead of bringing the unit down, I'm going to bring the unit up. So hour goes to the top, minute goes to the bottom. So 1 hour has 60 minutes. Hours can cancel. Now minute comes up. Seconds can go to the bottom. 1 minute has 60 seconds. Minutes can cancel. Now if I stop here, my unit is miles per second. I want kilometers per second. So now I can take miles and bring miles down here and go to kilometer. And the relationship there is 1 mile is 1.609 kilometers. And then my miles cancel. And I am left with kilometers per second. I do the math and I get 0.0291 kilometers per second. 28D, I want to go atoms to moles. So I have 4.58 times 10 to the 23 atoms. Mole is mentioned, so it's just 1 conversion. You need to know your relationships. That's 6.02 times 10 to the 23rd atoms is 1 mole, or particles is 1 mole. 22.4 liters of a gas is equal to 1 mole at STP. And the mass of a mole is equal to the molar mass. So I need to go atoms to moles. It's 1 conversion. Atoms comes down. Mole goes to the top. 1 is always going to go next to mole in these types of conversions. And I put 6.02 times 10 to the 23rd at the bottom. Unit atoms cancels. You need to know how to use your calculator. Either use the E button or the parentheses. If you get times 10 to the 46, you've done this wrong. And the answer should be 0.761 moles. If you're good with your exponents, you should realize that the exponent 23 cancels, and essentially it's 4.58 divided by 6.02. E, we have 17.3 liters, and I want to get to moles, and it does say at STP. So if it says at STP, it just means that you can use this relationship. Mole is mentioned, so it's only 1 conversion. Liter comes down, mole goes to the top. We're putting 1 next to mole, 22.4 liters on the bottom. And so I get 0.772 moles. F, we are going from grams of CO2 to atoms of oxygen. So this one is a bit more complicated. So I have 42.6 grams of CO2. When in doubt, get to moles. Okay, so first thing we're going to do is convert to moles of CO2. Now, to go from grams to moles, I need the molar mass. I pull out the periodic table. The molar mass of CO2 is 44.01. 1 carbon plus 2 oxygens. Once I'm at moles of CO2, I can go from moles of CO2 to moles of carbon, moles of CO2 to moles of oxygen, because this right here, the 2 and the 1, tell me a ratio of how many atoms there are per molecule, how many moles of atoms there are per moles of molecules. So now I can go 1 mole of CO2 gives me 2 moles of oxygen, and I get that from that subscript. Then what I can do is I can convert to atoms. So 1 mole of oxygen has 6.02 times 10 to the 23rd atoms. And then when I hit that into my calculator, 1.17 times 10 to the 24th oxygen atoms. And the last one, we're going from moles to grams. So 5.26 moles of copper chloride. Mole comes down, gram goes to the top. So mole is mentioned. So all we need to do is one conversion. You need to recognize that you use a molar mass. So it's 2 chlorines plus 1 copper. And the molar mass of that is 134.45. I get that from the periodic table, and I get 707 grams. Okay, so the electromagnetic spectrum involves energy that travels as waves that travels at the speed of light. And if I change the wavelength, I get different energies. So you need to be able to look at a graph or a chart of the electromagnetic spectrum and recognize that a shorter wavelength, which is on this side right here on this particular diagram, the waves are closer together. It also means a higher frequency. It happens more often. This is high energy. This is the high energy side. Okay, like gamma radiation is the energy, the radiation that we looked at with nuclear, that is going to cause the most amount of damage because it has the most penetrating power. On this other side, we have longer wavelengths, a lower frequency. This is the low energy side. So energy is related to wavelength and frequency. A short wavelength, high frequency is high energy. A long wavelength, low frequency is lower energy. Now for stars, you do need to know the difference of fusion and fission. Fusion is fusing together. Fusion is what happens in the stars. Okay, so in the stars, it is hydrogen fusion. Hydrogen fuses together to form helium. And in the web quest, you learned that this continues until a star reaches iron and nickel, and then it starts to collapse on itself. Okay, fusion is the fusing of nuclei, and it releases energy. The major factor, so if we look at the life cycle of the star, the major factor of which path is going to take is the mass. Massive stars, your larger stars, are going to continue down this path here. They can turn into your black holes, your supernova, etc. Your average or smaller stars are going to continue this way, and they would turn into the white dwarfs. So the mass is the most important factor in the path on a star's life cycle. I'm not going to spend a lot of time on Lewis structures because this is the last thing that we have done, but it's just a quick review to stress that you need to add up all of the electrons, do your electron count, and then work from there. So for CO3 2-, the first thing you need to do is add up all your valence electrons using your periodic table. So carbon's group 14, it has 4 valence. Oxygen's group 16, it has 6 valence, but there's 3 of them. And then it has a -2 charge, so I need to add 2 more. So my total electron count is 24. Then you need to draw your skeleton structure. And remember, typically the first element is in the center. If carbon's present, it's in the center. And the element that there's only one of will be in the center. So carbon is going to be in the center. I have 3 oxygens, so I connect 3 oxygens with a line. And each line represents a bond of sharing 2 electrons. So now this number is the total number of electrons that I'm allowed to use in bonds and lone pairs. I have used up 6 electrons, 2, 4, 6. So I subtract 6 from the 24. I have 18 more electrons to distribute as lone pairs. So I do 2, 4, 6, 8, 10, 12, 14, 16, 18, stop. Then you look, does everything have an octet? Well, oxygen does because it's got 8. Oxygen does, but carbon doesn't. So therefore, I do not have enough electrons to go around, and I need to adjust my structure, and I need to go back and add a double or potentially triple bonds or multiple double bonds. Now, I was 2 electrons short. For every 2 electrons you're short, you need an additional line. So I need to put a double bond in there. So now I've used up 2 more electrons. I have 16 pairs or 16 electrons as lone pairs. 2, 4, 6, 8, 10, 12, 14, 16. And then if it's got a charge, you put it in brackets. And that is the structure of CO3 2-. So the structure, I'll put it here. Remember to draw your dots neatly. Now to do the molecular geometry, you look at the total number of electron domains, or I like to say attachments, coming off the center atom, and then you determine how many of those are bonding attachments and how many of those are lone pairs. So I have 1, 2, 3 total things coming off. All 3 of them are bonds, 0 lone pairs on the carbon. This is trigonal planar, so it's a flat triangle. I am going to do HCN next, and then the other ones you can refer back to the answer key. So HCN, first thing we're going to do is we're going to count up our valence electrons. Hydrogen is group 1, carbon's group 14, nitrogen's group 15, so I have 10 valence. If carbon's present, it's in the center. Draw my skeleton structure. Subtract 2 electrons for each bond. So I have 6 electrons to distribute. You are never going to put a double bond or electrons on hydrogen. So I'm going to start on my nitrogen. I've used my 6. I'm done. If I look at the carbon, though, I need 2 electrons here and 2 electrons there. So I'm 4 electrons short, which means I need additional bonds. So if I'm 2 electrons short, I need 1 more line. If I'm 4 electrons short, I need 2 more lines. The only place I can put that is between the carbon and the nitrogen. So I'm going to subtract 4 more electrons. I can put 2 electrons as dots on the nitrogen. The nitrogen has 8, carbon has 8, hydrogen has 2. So my structure is this. Then I look how many total things coming off the carbon. I have 1, 2. So it's going to be 2 total attachments. 2 of those are bonds, 0 are lone pairs. That's a linear structure. For the rest of these, refer back to the answer key that is posted online.